Let's take a look at the multiplication rule, the basics. Multiplication rule is what we use in an AND probability. And we saw in the last section that if we were doing the probability of A or B, we have to take the probability of A plus the probability of B, and then we have to subtract the probability of A and B both happening. It was our formal multiplication rule. Essentially, the this formal addition rule. The intuitive addition rule was basically we count them up and we just make sure we don't count them twice. Well, if there was anybody that was in both categories, then we had to make sure we subtracted that. Well, let's look more in this section at the AND. How do we calculate that? Let's look at an example. If I flip a coin 2 times, what is the probability that the first flip is heads and the second flip is heads? Well, one way we can look at this, because we can actually write out the complete probability space, or complete sample space, all of the possible events, simple events that could occur. So here's our sample space. We could get heads and then heads, or we could get heads and then tails, right? Or we could get tails the first time and heads, or we could get tails and then tails. The sample space consists of 4 values, n equals 4. How many of those outcomes in the sample space would be successful? Well, there's only one where they're both heads, so the probability of heads is 1 out of 4. Well, the multiplication rule says intuitively that if 2 events are independent, and we'll get into that meaning in a little bit more later on, but basically it means that the occurrence of one does not affect the probability of the other. In this case, the second flip of the coin doesn't matter what the first flip of the coin was. It has no effect on the second one. But we'll come back to independent later. But if 2 events are independent, which these are, then the probability of A and B is equal to the probability of A times the probability of B. Okay, so when we did an OR, we added. When we do an AND, we multiply. Okay, that's kind of interesting. But of course there was an exception to the addition. If there's things that are counted twice, we have to make sure we accommodate and adjust our calculation. Well, similarly, if the events are not independent, which again we'll come back to, then we have to make some adjustments. But for now, let's focus on independent events. All we have to do is multiply. And well, we can check that with this situation. So the probability of the first one being heads and the second one flip is heads. According to this multiplication rule, since those events are independent, that should be equal to the probability that the first one is heads times the probability that the second one is heads, individually. Treat them as individual outcomes instead of let's do the trial twice. Let's do the trial once, what's that probability? Now let's do the trial once, and what's that probability? Well, with each individual coin toss, probability of getting heads is 1/2. And with the second coin toss, the probability is 1/2. And 1/2 times 1/2 is 1/4. Well, that certainly doesn't prove the multiplication rule, but it's evidence that supports it. Let's look at another example. And this one, we're going to find, we're going to roll 2 6-sided dice. Find the probability of getting 1 and 1, or snake eyes. Alright, well, we saw before in a previous section that an example with rolling 2 dice, the probability space has 36 different events. So it could be a 1 and a 1, or it could be a 1 and a 2, 1 and a 3, 1 and a 4, 1 and a 5, or 1 and a 6, or the first die could be a 2, and the second could be a 1, or a 2 and a 2, and a 2 and a 3, and so on. And all the way down to 6 and 1, 6 and 2, 6 and 3, and so on. 6 and 6, so that's 6 rows and 6 columns. 36 possible different simple events, so n equals 36. How many of those events have a roll of a 1 and a 1? Well, there's only one of them that's, snake eyes. So probability of a 1 and 1 is 2 out of 36, which would simplify, 1 out of 36. We don't add, yeah, so 1 out of 36 is only one simple event out of the entire sample space of 36 events. 1 out of 36. Now, we could also do this using the multiplication rule here. Since the 2 dice are independent, which again we'll get to a more precise definition later, but right now it's they don't depend on one another. They don't influence one another. Then probability that the first roll is 1 and the second roll, or second die, whatever you want to call it, is 1 would be equal to the product. Equal to the product of this. So the first roll is a 1 times the probability that the second roll is 1. And of course, if I roll a standard 6-sided die, there's 6 possibilities, and one of them is successfully a 1, so that would be 1/6 times 1/6, which of course is also known as 1/36. So we get the same answer either way. While we're here, let's take a look at the rest of the sample space. There's only one way to get a total of 2. There are 2 ways to get a total of 3. There are 3 ways to get a total of 4. We could roll a 1 and a 3, a 2 and a 2, or a 3 and a 1, and so on. And you work it all out, there's actually 6 ways of getting a total of 7. 1 and 6, or 2 and 3, or 3 and 4, and so on. So getting a total of 7 is the highest number of events, highest number of simple events that would result in rolling a total of 7. And that's why 7 is the most likely roll if you're rolling 2 dice. All right, let's do another example. This time we're going to look at a survey that we did in class, figuring out what everyone's favorite color is out of the 6 primary and secondary colors. And right now let's figure out what is the probability here's the trial here is select a random student, a random person. What is the probability that the first person selected prefers yellow, and the second selection prefers yellow? Okay. Well, the thing is here, these events are no longer independent. They depend on one another because the first person, if I successfully choose my first person who prefers yellow, there's only one other person left in the room who had yellow as their favorite color. So the probabilities have changed, the sample space has changed. For my first selection, there are 28 people that could be chosen, and 2 of them would be successes. So the number of successes would be 2. But if the first one is successfully a person who prefers yellow, prefers yellow, then for the second selection, the sample space has been reduced. There are only 27 people left in the sample space. And only one of them prefers yellow. Now technically, this question is a little ambiguous, and that's intentional. It depends on whether or not we make this selection with replacement. So really this is without placement. What that means is we select this person and then we don't put them back in the sample space. It's like if we put all their names on pieces of paper and put those pieces of paper in a box and we draw names. Well, if I draw out the first person's name, say one of these two people, these two females who preferred yellow, one of them was named Jennifer. Well, then if I don't replace Jennifer's name, there's only 27 pieces of paper left in the hat, and only one of them prefers yellow. And so what that means then is technically what I have here, it's affected. The first choice affects the probability of the second choice. So the probability that the second choice is yellow, given that the first choice was yellow, there's only one person left. 1 out of 27. So what we actually end up with there is that the probability that the first choice and the second choice, or first selection, I guess would be maybe a better word, first selection and the second selection prefer yellow. We still use the multiplication rule. We take the probability that the first selection is yellow, that's 2 out of 28, times the probability that the second selection is yellow is only 1 out of 27. We end up with 2 out of whatever 28 times 27 is. We take 28 times 27, 756, and then 2 out of 756 is 0.0026455, approximately. Okay. Now that was without replacement. We select the first person, and suppose her name is Jennifer. Then Jennifer is no longer available as a choice, as a possibility. So there's only 27 people left in the sample space for the second selection, and only one of them is successfully yellow. Now, if we make this selection with replacement, meaning we draw the name out of the hat, we look at it, we read it, and then we put it back in, well then whoever selected first could be selected again. And so the probability that the first selection is yellow and the second is yellow is equal to the product of those probabilities. It's still 2 out of 28, and the second one is also 2 out of 28, because if I put that first name back, if it's yellow, then I put it back, there's still 28 people, there's 28 names in the hat, and there's still 2 of them that are yellow. So here's the formal multiplication rule. The probability of A and B is equal to the probability of A times the probability of B given A. So we put a vertical line there. So what this means, probability of B given A, that's the probability that B occurs, really assuming A has already occurred. So in the case of our without replacement thing here, we're selecting two people in the room. Probably the first one is yellow and the second one is yellow. When we weren't replacing them, then this 1 out of 27, that was really, that's the probability of selecting someone who prefers yellow, given that the first choice was already yellow. If the first choice is already yellow, then there's only 27 people left in the room, and there's only one person left who prefers yellow. So 1 out of 27, in that case, would be the probability that the second choice is yellow, given the first choice was already yellow. If the two events, when we did it with replacement, it didn't matter that the first selection was yellow. So this one was still 2 out of 28 because it didn't matter if the first selection was yellow or not. I put whatever name it was back in the hat, so the second choice is still 2 out of 28 probability that it'll be yellow. Okay, well, let's formally define independence here. Okay, two events, A and B, are independent if the occurrence of one does not affect the probability of the occurrence of the other. Otherwise, they're called dependent. So, in the case of selecting the people that prefer yellow, if we are putting the name back in the hat, we're doing it with replacement. We're replacing whatever that first choice was back into the sample space. Then the fact that the first choice was yellow, if that occurrence, right? An occurrence, if that occurs, if event A occurs, if the first choice is yellow, that does not affect the probability that the second one could be yellow, if I'm putting the name back. But if we're doing it without replacement, right, if we're doing it without replacement, so we don't put that name back in the hat, well then there's only 27 people left and only one of them prefers yellow, so that changes the probability of the second choice. So if the first one occurs, if the first person chosen does prefer yellow, that affects the probability that the second person will also be yellow, if we are not replacing the names. Now, we need to be careful with the word dependent. Okay, so here's a caution. Dependent. Dependent? That's not how you spell it. Dependent does not necessarily mean that one causes the other. It could, but not necessarily. Does not necessarily mean that A causes B or B causes A. That's a common misunderstanding of this term, dependent, independent. So as an example, let's look at this. Consider these two events. Event A is that the microwave won't turn on. I go into the kitchen, I try to use the microwave, and it won't work. And event B is the refrigerator isn't working. I open it up, the light's off, and it's not humming, it's not doing its job to keep things cold. Well, neither one of these events would cause the other necessarily, although it's possible that one of them blew the fuse. That's possible, they could cause one another, but they don't necessarily cause one another. But if one of them happens, it increases the probability that the other one would happen, because if the microwave won't turn on, there's a good chance that the power's out or a fuse is blown somewhere. And if that's the case, then the probability that the refrigerator won't be working is much higher than normal. Still not guaranteed, because maybe it's a different issue. Maybe the microwave just broke on its own. So it certainly doesn't guarantee anything. But we refer to these events as they're not independent, they're not completely separate. I'm not sure dependent is the best choice of words there. They're just not independent. But they're certainly not completely reliant on one another, but they rely on some common cause, or they could be relying on some common cause of the power is out, or the fuse is broken, blown, whatever. So, dependent events do not necessarily cause one another. They just have some association, so that if one of them happens, it makes it more or less likely that the other one is also happening or going to happen.